Hi, my name's Kevin Starr. I've been asked many times, how do I tune a loop? So what we're going to do is take about 15 minutes and we're going to give you the bare minimum requirements in order to tune a loop. The thing with automation, if you've ever heard this idea of the tip of the iceberg, what we're talking about is automation continues well under what you see. What's interesting is at the very top is there's these three little numbers called PID. And how do we set those up? It seems very easy, but it's sort of a little bit like trying to balance bowling balls. You know, it's how do you do that? That's what we're going to talk about here in just a few minutes. Recognize that there is a lot of information under the surface. And if you want more detailed information, we have books, we have presentations. I liked it so much, I went back to school and got a master's in automation. So what we're going to do is spend a little bit of time talking about how to tune a loop. Now what we have to do is we have to start off with this thing called a controller. That controller, it actually has an output, and it will talk to, I'm just going to draw a, let's call that a valve. That's a valve. And this valve, let's say there's some process here that we're controlling. And this process, it has some sort of a, you know, an I/O module or a transducer or something. It's a sensor. And that sensor produces some sort of a feedback signal, okay? So what we have is this controller that takes the measurement, and we call that the measured value, and we have an output, which we call the output. Now what we need also is a reference. So this is our reference, or we call that our set point. So our set point is what you want. That's where I'm trying to, like the room, this temperature, I want it to be at, you know, 68 degrees, and if it gets too hot or too cold, the furnace kicks on to adjust it. So what we're looking at here is with our process. We have a control sending an output to an actuation device. That actuation device could be a valve, it could be a drive, it can be an actuator, and you need to go and do a visual inspection. So when you're walking up to a process, do a, let's just put it, a visual inspection. That's what I like to do. I was at one site and they said, can you tune this loop? I said, well, I need to go look at it. And they're like, this guy's going to fix our problem. And they're like, why is that? I said, because you're the first one to ask to go out and see it. So I like, if it's safe, go out and have the operations or whoever the operators are take you and show you the valve. Take a look at the condition of the valve. What's it look like? Has it got an I to P converter? Has it got a P to I converter? Does it have a valve positioner? Does it have a cam? Is it rusty? Is it a single seated globe or a top hat or a rotary valve? Look at it. Is it rusty? Then you know you're going to have a hard time. Then go over and look at the sensor, or look at the device, the transducer that's converting it from a measurement to a signal that can be transmitted back. What vintage is it? Is it old? Is it a mag flow meter? Is it a pitot tube? Is it an orifice plate? Is it a differential pressure device? Try to figure out, just take a look at it and kind of get an idea of what you're looking at, because you're after the numbers in this are those P, I, and D. You know, and we're going to talk about what those things are. Now, the class of process that we're talking about, there's several different things. We can talk about flow, pressure, temperature, consistency. These types of processes are what we refer to as self-regulating. That's different than what's called a tank. In this particular short talk, we're just going to talk about self-regulating. This represents, this list is probably 80 to 90% of all the industrial loops that you're going to run into. So if we get this, you've got yourself pretty well covered. So the first thing you do is do a visual inspection. Look at the valve, look at the sensor, look the thing over. Second thing you want to do is do a bump test. So what's a bump test? Well, what we're going to do here is we're going to come down here and we want to inject energy. We want to do a step change. This is what's called a step. And what we're going to do is we're going to have a change in this thing called output. This little triangle is a change, or it's a delta. It's the change in the output. And what we're going to do is, typically we put the control in manual. So in manual, or we want to adjust the output so that we can inject a step. And there's a lot of restrictions depending on the industry on how big of the step you can make. I always recommend start small and grow and get larger. We also recommend a step cycle where if this is 1x, this is 2x, and then you come back up. So what happens if the operator says you can do a 5% change, you go up 5, down 10, back 5, and then this is where you can do your identification on. So what we're looking at is we do this bump test, and at the same time we want to record the measured value. So we want to record this, we want to find the relationship, and that's what we call modeling. So we want to model, or it's called identification. Identification. So we want to come up with the model parameters. You have to capture the dynamics. You have to be able to say, if I move this, what happens? And you have to repeat it and make sure that you understand what those parameters are. Once you have these parameters, the next thing you do is you come up with tuning. All right, and that's what you need. Tuning is when you come up with the numbers for these P, I, and D. So you do a visual inspection, you do a bump test, or more than one. You do a model identification to calculate the parameters. You use those parameters to come up with tuning, and then I always like to stop at a validation step. Make sure validation is do a closed loop set point change. Go and change the thing. Change the set point and see what happens. You're the one in control. You're the automation engineer. You're the one that did all this thing. You're the one that tuned it. When you change the set point, it ought to work. Now let's quickly go through here. The bump test we talked about. Now let's talk about modeling. What we're talking about when we do a model is, let's do a little block here. We'll call this our process. Okay, so here's where I made my step input, and then we get this response. This is the question mark. How do we identify that? What is it? How do we find it? Well, if you can trend this, it's better. If you can store the data in a text file and load it into an analysis tool or Excel or our loop tune. But in the worst case, you can do a bump test and then watch the process. Okay? And what I'm trying to show you here is it's a simple first order model. With a simple first order model, what you're looking at, and I'll put in some parameters here, this is our change in our output. This is our change in our process variable. And this is our change in time. Remember, that little triangle means delta or change. So with those three things, that's what I like to think about for the easiest case is how much did it move for a given change and how long did it take to get there. So we're looking at two things, is the process gain is defined as K sub P, which is equal to the change in measured value. Let's see that, let me change that to PV, over the change in the output. That's simply what it is. This is answering the question is how much did it move? So how much did it move? That's the first thing. You can get that pretty easy. Just take a look at the change and how you change in output over the change in process over the change in output. Second thing you need is the time constant. That thing's got this funny looking symbol, tau sub p. Tau is a Greek symbol that universally represents the time constant. Tau sub p can be approximated as the change in time over over 4. So it's the change in time over 4 approximately. Now there's a couple ways to do this. You can sort of take this and divide it into fourths, or you can say, okay, take this total time and sort of divide it into thirds. Sure enough, right there it is. That's roughly 63.2% of where it's going to go. So how long did it take is one time constant. So 1, 2, 3, 4, you're pretty much there. So in this, you can do this with a Timex, your watch. It's hard because in a real world, you've actually got a process that may be wiggling and jiggling. It may, kind of doing this type of stuff. But no matter what, it'll stop. So what I like to do is sort of draw a first order model on my response, look as far out as I can to get the process gain, and then see how long it takes to get there to get my change in time, and that's my time constant. These two parameters, this and this, are crucial. You have to make sure you've captured them. You make sure you get those. So do another bump test and see. If these change every time, then you've got an actuator problem or a process problem or a nonlinearity issue that you have to investigate. If you can't predict what's going to happen when you change this output, then this controller has no chance of getting it right. So make sure that after you've done the visual inspection, after you've done the bump test, take a look at the model and make sure it's repeatable. Now we've captured the dynamics. Now we're ready to do tuning. So now we come over here and let's talk about tuning. First thing we have to do is recognize that not all PID algorithms are the same. There's actually three classes. There's standard, parallel, and classical. They have to do with how the algebra behind the scenes works. And I'm not going to go into that right now. We're going to work with this one right here. And it has a thing, looks like this, 1 plus 1 over. This is what it looks like. So I would recommend you go and take a look at your technical reference for your particular vendor, and you'll see a mathematical expression. Well, I'll just show you. The parallel one is going to be this plus Ki over S plus KDS. I guess the reason I like this one is these happen to be my initials, KDS. Now, and then classical looks like this. It takes KC, 1 plus 1 over TIS, and then it multiplies it by 1 plus TDS. So what I recommend is, I know this is a lot of math, but this is what the control modes look like, and I always have to go and look in the reference guides for our particular vendors. And whether you work, I won't name all the vendors, but not everybody calls everything the same thing. Some it's an integral time, some it's an integral gain, some it's a proportional band, controller gain, derivative time, there's a derivative filter, all those different caveats. But if you look at the equation, look for the parentheses, and then that will tell you what type you have. For the analysis that I'm going to use, I'm going to assume the standard algorithm. My brain kind of was tied to that. It's not that it's that difficult to convert, but I always work towards standard and then I convert it to the parallel or classical forms. One other little hint is if the derivative time is set to 0, notice that these are identical. So you may have a classical or a standard, but if you're not using derivative, these two are the same. So what I wanted to just point out is I've seen too many places where they'll change a DCS system and they'll go from parallel to standard or classical, and the guys that tune by feel, these numbers can't work. If you just take this number and stick it here, it's not going to work. Actually, it could blow up. So you have to recognize what kind of controller you have. But once you have it, then you get into the tuning rule. And there's whole different theories on, do you want a first order response, a second order response, do you want to have Ziegler-Nichols, do you want to have, what do you want? Well, I think for what we're talking about here is I want a first order closed loop response. You're the guy that's doing the tuning. You set it. So what we're saying here is if I change the set point, I want my measured value to come up in 4 closed loop time constants. So here's a question for you. Notice that the change in measured value equals the change in set point. So what's the process gain in the closed loop form? So here we're changing the set point. Go back over here. This is where, just so where we're at, is we're now injecting energy into my set point. The loop is in auto, and I'm changing the set point. Over here, our loop was in manual, and we changed the output. This is called a manual bump test. Here, we're doing a closed loop bump test. And this is the set point. So the whole thing becomes live, and that's what we're after here. So what we're saying is when I change the set point, I want the measured value to respond in this particular shape. So in this case, the closed loop gain is the change in measured value over the change in set point, which is equal to 1. And the time constant is equal to the time constant. It's this total time divided by 4. So that's what it is. So what is the tuning rule to do that? There's a lot of math, remember, underneath the surface, but the control gain is equal to 1 over the process gain times this thing called tau ratio. And the integral time is equal to the process time constant, and the derivative time is equal to 0. This is the magic numbers that you have to use. So notice that the tuning is a function of your model parameters, and this thing we're calling tau, my blue marker's dying, is called tau ratio. Tau ratio defines speed. And let me just take a second and tell you what that means. Tau ratio is defined as the closed loop time constant divided by the open loop time constant. So people will talk about fast or slow, and I don't like to do fast or slow. When you use tau ratio, it balances. This is fixed. This is your process. So when you say fast or slow, it has to be as a function of what's real. So I like to use tau ratio of, let's say, if we make a table, let's just make a table. Tau ratio, and let's talk about speed of response. If we say 1, that's what I would call very fast. And then we'll go with 2, 3, 4. 4 is very slow. This is safe. And this is, I would say, marginal. It's just fast. Faster, fast. So your speed of response. So this tau ratio is really just a knob. You decide how fast you want this to run. So if you had a 6-second open loop time constant and a tau ratio of 2, you would have a 12-second closed loop time constant. So for example, let's do an example now. Let's say we did our inspection and looks good. We did our bump tests, manual, looks good. We did our model, and we got a process gain of, let's say, 2.0, and we say a time constant of 6. Looks good, and we could get that every single time. Let's say that we want our tuning, and we want let's say it's aggressive. Let's say we want to go safe. I always recommend start with the safe. So what we would say is that our controller gain will equal 1 over Kp tau ratio. So that's going to be 1 over 2 times our tau ratio of 3. So that's going to equal 1 over 6 for our control gain. And our integral time is just going to equal 6. Boom. So those would be your tuning numbers. So then the validation. Now you do the validation. Validation is in closed loop. You change the set point. What should happen? Well, your process, if I can get a little bit of life out of my ink pen, it'll start to come up. Ooh. How long should it take to get there? Well, it should take 4 closed loop time constants, but we said that we had a tau ratio of 3. So what would be my closed loop time constant? It should equal my tau ratio times my process time constant. So I've got a time constant of 6, tau ratio of 3. So that's equal to, what is that, 18. I should have picked a little easier numbers. So my closed loop is 18. So 72 seconds is how long it should have taken to get there, because I have a closed loop time constant of 18. And it should go whatever I told the set point to do. The other neat little thing is the output. This is the total change needed. This is the change in the output needed. This first step, this first kick, if you will equal the total output needed divided by your tau ratio. So in this case, it would be 1/3. So that would be, so the result would be, the kick will be 1/3 of final, delta. So I almost got that drawn right. So this would be 1/3, and then it gets there the rest of the way. So with this, you can actually come up, and then you can walk away and you know this thing's tuned. So we just went through the whole step here on the board of talking about the process, modeling, tuning, how to pick speeds, and then how to validate it. You do this, you'll have a loop that will run very, very well. will be stable. It won't be calling you in the middle of the night. And if something does break, it's the theory that does not break. That means something broke. The assumptions weren't right, the models changed, the actuator got stuck, but you will have a paper trail that you can record, do a bump test, and you'll see what changed. That's how you do tuning, and that's how you tune a self-regulating loop to have a first-order closed-loop response. The video you just watched literally represents the tip of the iceberg in the space we call process automation. If you'll give me just one more minute, I'm going to show you where you can get more information on this topic. We've actually written a book called Single Loop Control Methods. We have a training course that you can go to ABB University to learn more about through formal instruction. We have a virtual environment version of the same course that you can take at your own pace. And we not only have the knowledge that we're making available to you on the lessons that we've learned over 50 years of automation, we have tools and services that can help you, that you can use to improve your process. One of them is called Loop Tune. Loop Tune is a package that you can run on your computer that will collect data, you can do the bump test, and you can analyze the things that we looked at in the video and have a report and have a record and do simulation before you actually try it in the real process. That's called Loop Tune. This box I'm standing beside is called ServicePort. It comes in several different form factors, but it is designed to plug into your automation system and evaluate the performance of these control loops so that you can quickly identify problems and fix them so that you can have increased improvement of your process. For more information, go to the link in the description below. Thanks.